So let's suppose now what we're going to look at is we're going to talk about the last little piece of um, calculating limits, right? And we're going to utilize this thing called the squeeze theorem, which is a theorem. And the cool thing about this theorem is that it doesn't really like necessarily give us the value of a limit, but it leads us to the value of limit logically, so that there's no other choice that we have other than this. This is in fact the case. Okay. So let's suppose that if I have an f of x, right, which is less than or equal to g of x, which is less than or equal to h of x. So let's say, for example, that g of x is right in between an f of x and an h of x. Okay, so like we got these two functions, and on one side you have f of x, right? That's going to be your lower end, and then you have g of x, which is going to be your upper end, which is above that, and then you have h of x, which is on top of g of x, and they kind of squeeze in, right? That's the whole idea of the squeeze theorem is that they're going to be like this. They're the bread, and g of x is like the meat in the sandwich. Okay, and that's what it's saying, right? The idea one of those functions around a is always more than the other function around a. Okay, except possibly at a, right? But we're going to show that it has to be. So we'll find the limit that x approaches a of f of x is equal to the limit as x approaches a of h of x, then that's going to equal L. Okay? Then the limit of g of x as x approaches a is equal to L. All right? So basically, if we've got f on the bottom, h on the top, g in the middle, okay, if we know that the two on the top and the bottom, right, are the same, they're going to squeeze out, and that's going to mean that g of x has also got to be equal to that same limit. Okay? We're going to show how this kind of works, right? You got to think about that. It's a thinker. A lot like when we talk about the precise definition of a limit. So let's take a look at an example. So let's find the limit as x approaches 0 of x squared times cosine 1 over x squared. So what we have here is we say, okay, well, I'll tell you what, I know that cosine of 1 over x squared is greater than or equal to negative 1 and less than or equal to 1, because the range of cosine is negative 1 to 1, inclusive, right? So what that's going to mean is that's going to mean then that if we take, right, I multiply x squared by both of them. So I say, okay, well, multiply x squared by x squared. Everything. I get now negative x squared is less than or equal to x squared cosine 1 over x squared, which is less than or equal to x squared. Okay? That's true, right? I just multiplied by x squared on both sides. X squared is always positive. Cool, no problem. Well, the limit as x approaches 0 of negative x squared equals 0. It's a polynomial. 0's in the domain, just substitute. And the limit as x approaches 0 of x squared is equal to 0. Okay? Well, there it is. So this one is right in the middle, right? That's my g of x, right? So by squeeze theorem, x squared, the limit as x approaches 0 of x squared cosine 1 over x squared is equal to 0. So all I used was I used that theorem. That theorem said, well, if I can prove that I've got the two functions that are on either side of my function, my g of x, right, and they have the same limit, right, they're equal to each other, they're both equal to 0, then the limit of my middle function has got to be the same. Okay? This is definitely one of those ones where you're going to want to spend some time not just thinking about it, but reading it, maybe reading some different examples, asking some examples, like working through problems in class, right? So that you can go in and then do this on your own. It's not like algebra. This one is not like algebra. You have to understand what the theorem is saying and then apply kind of basically the steps of the theorem. Okay? So that is the squeeze theorem.